So let's go then to some applications. In particular, I'd like to discuss increasing functions and actually also decreasing functions and the relation that has with derivatives. And also we'll go into second derivatives, so higher order derivatives, in particular concepts known as convexity or concavity of functions. So there's a whole range of applications, so I'll skip the first two of those in this lecture so you can read about those in the book. So one is about rates of change. So we saw that derivative actually measures how fast something changes, right? How fast a line, for instance, the height of a line or the height of a curve changes as you move to the right on the x-axis. So that's basically similar to what in real life you might like to call speed. So speed is how fast does location change as you change time. So indeed speed is also defined as the derivative of location as a function of time. So have a look at that chapter. So tangents should be no surprise in the sense that we derived or we define the derivative or we define differentiation in terms of the slope of the tangent line. So if you are interested in what's the slope of the tangent line to a function, then indeed you're interested in the derivative of that function at that point. So have a good read of that chapter as well. What I'll do now in this video is look at increasing and decreasing functions and that convexity or its counterpart concavity. And then the next part, which we'll do in more detail, but in the next lecture only, we will extend that into optimization. So we're going to ask when does a function attain its maximum or its minimum. So that's optimization, and it uses again differentiation. So let's go first to increasing or decreasing functions. So what does that mean? So let's look at some function defined on some interval. It's called the interval I. So it's all the x coordinates between two boundaries, which might or might not be included in this interval, as we know. So, and not surprisingly, a function is going to be called increasing if the function is going to be higher at coordinate x2, which lies to the right of x1, than it is at coordinate x1. So as you move to the right, the function gets higher and higher. Yeah, that's what you would expect to be increasing. There's a slight subtlety here because you see in this definition, the function value at this more advanced point x2, so to the right, is asked here to be higher or bigger than or equal to f at x1 at the left hand point. So if the function is actually flat, so in normal daily usage we would say this is a flat function, not an increasing function. Mathematicians still would like to call this increasing. So you see this graph at the bottom on the left hand side. This function is flat for a bit, in the left hand bit, and then actually it makes a jump, and only then does it start increasing strictly. So we would call this an increasing function because even where it's flat, this left hand bit which ends at this open part on the right, we would still call that an increasing function if we really mean that it should be increasing, not even flat. So we want this function to be bigger than, if we go to the right, we want this function to strictly grow, then we call this thing strictly increasing rather than increasing. So that's just a mathematical definition question. So now you can imagine that there is a relation between increasing and also strictly increasing and the derivative of a function. So what is this relation? Well, if on this interval that we are looking at, so for all x in the particular interval that we're interested in, if the derivative of this function f prime of x is bigger than or equal to 0, that's the first remark over here. If that's the case, then we know that f is increasing on that interval, and vice versa. If f is a differentiable function, so we can define this derivative actually everywhere, and we are told it's increasing, then we also know for sure, well, its derivative must be bigger than or equal to 0 for all x in this interval. So that's the first bit. The second bit is about strictly increasing. If we actually know that this function has a positive derivative, so not just non-negative but positive, so bigger than 0, 0 itself is not included then. So if f prime is bigger than 0 for all x's in this that we choose in this domain, in this interval domain, then we call this function to be strictly increasing. And you see here actually there's this difference between these two signs. So here you see this arrow goes two ways. So it's both true that if f is increasing in I, then f prime is bigger than or equal to 0, and vice versa. So if f prime is bigger than or equal to 0, then we know for sure that f itself is increasing. For the second one, this is actually not completely true. So if we know that f prime is bigger than 0, then sure, f is strictly increasing. But actually f might be strictly increasing even though f prime might be 0 at some point. And we see an example here. So this function over here is strictly increasing. The further to the right you go, strictly higher the higher and actually strictly higher this function is. But at these ends you might see that this function is actually in this precise point it's flat. At least it looks flat. So if in an isolated point f prime equals 0, then still this function will be strictly increasing if at all points surrounding that isolated point the derivative is going to be positive. So that's a slight nuance here. Of course, all that we said about increasing, we can also say about decreasing functions. So here also, of course, we also have a decreasing and a strictly decreasing function. So this function is decreasing because though it's flat here, that's allowed. It's smaller than or equal to the function evaluated at the point further to the left. While on the right hand side, this function is strictly decreasing. So if you go to the right, this function strictly declines, it strictly goes down. And again, there's a similar relation between derivatives and f being decreasing or strictly decreasing. So if f prime is smaller than or equal to 0 for all the x's in this interval, then f must be decreasing and vice versa. And if indeed we know that f prime is smaller than 0 everywhere, then f is actually strictly decreasing. But again, this is not a two-way relation. So again, here you see this function might actually be in this singular or in this individual point at the end, in this case, of the interval, the derivative. Well, we might guess here because we cannot compute, but from the picture it looks like it's completely flat in this one point, and in this individual point, well, still this function is strictly decreasing. So let's have a look at one or two examples. So here's a simple example. This is a quadratic, the simplest quadratic function that we can imagine. K of x equals x squared, which is defined on the whole for any x. So the domain is the whole range of, the whole domain of real numbers. Can we determine the derivative? Yeah, of course, because we know what the derivative of a power function is. So this is nothing but the power function with the power is 2. So what do we need to do to compute the derivative? Well, we bring down this exponent, this power, put it in front and lower the power by 1 to get just 1. So the derivative is going to be 2 times x. We've seen that before. So what can we conclude here? Well, as long as x is bigger than 0, this derivative is going to be bigger than 0. And actually, if x equals 0, the derivative is 0. So on the right-hand side of the domain, for any x bigger or equal to 0, this function is going to be increasing by the logic that we had before. And likewise, if we look at the left-hand side of the domain, so for x smaller than or equal to 0, there we can immediately see if you plug in x is smaller than 0 or equal to 0, then k prime, the derivative, is going to be smaller than 0 or equal to 0 itself as well. So we know that k is actually a decreasing function for all the non-positive numbers. So for x smaller than or equal to 0, k is a decreasing function. Okay, does that make sense? Well, yeah, it does, of course, because this is, of course, the graph of that quadratic function. And we see that on the right-hand side, k is this increasing function, going up everywhere, whereas on the left-hand side, k is this decreasing function. Let's then look at one other example. So let's look at the cubic function, x to the power 3, again a power function. So you can again use this derivative to compute what its sign is. So is it positive or negative or perhaps 0 at some point. And from that again we can deduce that for which intervals this function is going to be increasing or decreasing perhaps. So let's determine the derivative of this cubic function x to the power 3. So again what we need to do is bring the power in front of the expression with x and lower the power by 1. So that gives us the f prime. The derivative of this function f is 3 times x squared. So what can we say about that? Well, f prime is going to be bigger than 0 since x squared is it's a square, like I say. So this is going to be bigger than 0 both for x is smaller than 0 and for x is bigger than 0. There's only a single point in which actually f prime equals 0, and that x equals 0 obviously. So since it's only the single point where the derivative is 0, and in all other for all other x f prime is going to be strictly positive, this function f is going to be strictly increasing for all x. So that's what we learn again from the derivative, and we can also see that it is true or makes sense if we look at the graph, because what's this function f itself is the blue line. X cubed x to the power 3 looks like this. It goes up here, it goes flatter and flatter. At 0 itself, it's completely flat, and then again it starts rising again. So the purple line here is 3 times x squared, which is the derivative of this blue line, of this blue curve. 3 times x squared, and we see indeed this is everywhere above 0. It's always positive except this single point, x equals to 0. So that's increasing and decreasing. The second part of this application that we wanted to go into is about convexity and concavity. And in order to introduce that, we have to actually make one further step, extending what the derivative is. So again, let's look at some function defined on some interval I. Then we've seen f prime, that's the first derivative of f. But we can also take, f prime itself is a function, right? So we can take the derivative of that function. And also that has a name, that's called the second derivative of f. So the derivative of f prime, so the derivative of the function f, that's called, not surprisingly, the second derivative of f, and the notation that we usually use for this second derivative is f double prime. So that's this thing. Now what does f double prime, the second derivative, tell us about a function? Well, actually it tells us whether it's convex or concave on a certain interval. So what's convexity? Convex essentially means it's hollow in this sense. So if you look at the slope of at the derivative of this function itself, you see here it's negative, keeps growing until it's 0 over here, where it's flat, and then it keeps growing further and gets bigger and bigger. So it keeps growing and growing faster. So that's what we call convex, and that's identified essentially with the second derivative being bigger than 0 for all x in this interval. And the opposite of convex is we call concave. So concave is like this inverted U-shaped form. So the slope at this side of the function is pretty high, so it's increasing pretty fast. It goes down and down and down. Here the slope is actually 0, so the function itself is flat. And it keeps decreasing, so here the slope gets negative and we'll get more negative over here. So this is what we call concave. And concave relates to the second derivative again, as if the second derivative is always smaller than or equal to 0 on this particular interval, we call f concave on this interval. And often we are actually also interested in this interval being the whole domain on which the function is defined. So if f is convex on its whole domain, then we just say f is convex, period. Whereas if f has a negative or 0 second derivative on its whole domain, then we call f a concave function. So let's have a look again at an example. So again, let's look at the same power functions that we had just a minute ago. So here's this quadratic function. So we could determine the first derivative. We did that. So f prime was 2x. No difficulties there. Can we now also determine the second derivative? Yeah, no problem. We just have to again take the derivative of this f prime. So can we take the derivative of 2x? Yeah, sure. It's just 2, right? So the derivative of x is 1, and therefore the derivative of 2 times x is going to be 2. So the second derivative of f double prime equals 2, it's actually a constant in this particular case, is also a positive number. So for any x in R, any real number x, the second derivative of this function is positive. So by the definition that we just had, we call this function convex for all x in its domain R. Well, let's actually look at this graph that we had. So we had the graph of x squared over here. And indeed, this has this U shape that we call convex. So this is a typical convex function. So let's go to a second example here. Let's look at the function g. So g is a quartic function. It's minus x to the power 4. So again, this is a power function, so we can take derivatives. So let's do that. Let's take the first derivative. So g prime, the first derivative of g, well, take down the power 4, reduce it by 1, x to the power 3. So we get g prime equals minus 4 times x to the power 3. That's the first derivative of g. Well, then it's a small step to also take the second derivative, because we just have to take the derivative again of minus 4 times x to the power 3, which is again a power function. So x to the power 3, put the 3 in front, well, it multiplies the minus 4 that we already had, so that gives us minus 12. And again, we reduce the power 3 by 1 to get 2. So g double prime, the second derivative of g, that's just minus 12 times x squared. So can we say something about the sign of g double prime of the second derivative of g? Yeah, sure, because x squared is of course going to be bigger than or equal to 0, because it's a square. Squares are always 0 or larger. So g double prime is minus 12 times this square. So it's going to be smaller than or equal to 0 for all x. And by that previous definition, smaller than or equal to 0 everywhere, g is going to be a concave function on its whole domain of all real numbers. So what does the function g actually look like? So that's a right-hand function. So the x squared function that we looked at, the convex function, is the left-hand one. The right-hand one is f equals minus x to the 4th. So that second example that we just looked at, and indeed this is this inverted U shape, if you wish. It's kind of a hill type function. And these types of functions are called concave. And indeed, concave is nothing else but saying that this function has a negative second derivative everywhere. So the next video will be about how can we compute derivatives in a convenient way for combinations of different functions. So we'll look at sums, products, quotients of functions, and we also look at composite functions and the chain rule.